the core idea. A double bond is packed with electrons. It's electron-rich. That makes it a nucleophile. And it's naturally drawn to anything that's electron-poor, an electrophile. This fundamental attraction, this pull, is what drives countless reactions. And it all happens in this beautiful two-step dance. First, the pi bond, with all its electrons, attacks the electrophile. This breaks the pi bond, but it leaves one of the carbons with a positive charge. We call that a carbocation. So what's step 2? Well, a nucleophile, like the bromide ion that got left behind, sees that positive charge and captures it. Attack, capture. That's the pattern. That's the dance.
Okay, so you might be asking, where exactly does the electrophile add? This brings us to Markovnikov's rule, which you've probably heard taught as the rich get richer. The hydrogen adds to the carbon that already has more hydrogens. But listen, this isn't just some arbitrary rule to memorize. The crucial part is why it happens. It's because that specific pathway creates the most stable possible intermediate. And this is that why. Carbocations are unstable, but they can be stabilized by their neighbors, the carbon groups next to them. A tertiary carbocation, connected to 3 other carbons, is the most stable. It's getting the most help. A primary one is the least stable. And here's the thing about reactions. They're kind of lazy. They will always try to go through the most stable, lowest energy pathway possible. That's why Markovnikov's rule works. It's not magic. It's just stability.
Okay, so now we understand the default pattern. We know what the reaction wants to do on its own. But what if we don't want the default product? This is where organic chemistry gets really powerful. This is where, by choosing our reagents, we get to be the director of the reaction.
Let's see this in action. Say we want to add water across a double bond to make an alcohol. If we use simple acid and water, we follow Markovnikov's rule. No surprises there. The OH group adds to the more substituted carbon. But check this out. If we use a different set of reagents, this is hydroboration oxidation, we can actually force the OH to add to the less substituted carbon. See that? 2 different sets of reagents, 2 completely different products. You are in control.
Here's another classic control problem for you. If you just add regular hydrogen gas to an alkyne, it doesn't want to stop. It'll reduce it all the way down to a single bonded alkane. But what if you want to stop halfway? What if you want the alkene? How do you do that? Well, if your goal is a cis alkene, that means the hydrogens end up on the same side of the double bond, you use a special tool. It's a poisoned catalyst called Lindlar's catalyst. Basically, it's just reactive enough to add 1 molecule of hydrogen, but it's too weak to go any further. And because the reaction happens on the flat surface of the catalyst, both hydrogens have to add from the same side. And just like that, you get your cis product, specifically. So what if you want the trans alkene, where the